The Fermi Paradox asks a simple question with a complicated answer. If the universe is so vast and old, and life seems likely to emerge, then where is everybody? It's a mystery we've explored many times on this show, sometimes seriously, sometimes speculatively, and occasionally with a bit of a laugh. There are dozens of proposed explanations, ranging from the sobering to the downright strange. We even did a 3-hour compendium of them, which is still a short summary, and today I'll be sharing 5 that I find especially compelling, and 7 that, frankly, I could do without. Or at least, I wish they were less popular, because their reasoning or evidence leaves a lot to be desired, even if they sound great at first. I know in most top 5 or top 10 lists, you're supposed to save your number 1 pick for last to keep folks watching, but in this case, I think we need to start with the number 1 on both ends, because they're essentially the default answers to the Fermi Paradox, and honestly, I haven't ranked the rest all that precisely anyway. Since I have got more explanations I dislike than I like, let's start there, with what's arguably the original Fermi Paradox solution. And that's the idea that space is just too big to colonize. As the Hitchhiker's Guide to the Galaxy puts it, space is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is. That was more or less the reasoning given by Enrico Fermi himself, though it was others who coined the term Fermi Paradox, usually while arguing that he was wrong. Fermi, best known for helping to develop the first nuclear reactors and weapons, didn't live to see the optimism of the space race. He made his now famous remark during a time when nuclear war seemed more likely than starships. And his era's explanation, that space is just too vast to cross, became the foundation for what we now call the 2 primary late filters in the Fermi Paradox. Either civilizations destroy themselves, or they're simply unable to expand into interstellar space, or maybe conduct a few attempts to neighboring stars that are such marginal successes at best that nobody sees as a point in trying again. And keeping in mind that 56 years ago we landed on the moon, did it 6 times over the next 3 years, and haven't done it since, this explanation can resonate too. The idea that interstellar colonization is just impractical seems legit. After all, the moon is only 250,000 miles away, Mars is 100 times farther, and the nearest star system is over 1,000,000 times that. Even if you somehow pack up the tools and tech to survive a centuries or millennia-long voyage, when you arrive, you're faced with the challenge of making an alien planet livable, and then doing that again and again, millions of times over, just to make your mark at a galactic scale. It sounds daunting, and yet I, for one, am not daunted. And if you are a channel regular, you probably know why and feel the same. More technology would help, a lot. We already have the tech we need to get out and develop space, and once you've established a true presence there and given it time to grow, then building giant arc ships able to survive the journey to another solar system gets a lot more plausible, and those are not just your transports to another system, they're your beachhead too. You refuel them as needed, whether with deuterium, uranium, or by simply unfurling solar panels, and likely expand on them while settling each new solar system. In this way, these arcs, usually envisioned as enormous rotating habitats, can orbit any star and allow for settlement on a far grander scale than merely colonizing planets. This concept has been core to the vision of the National Space Society, which I have the honor of serving as president ever since its founding decades ago. It's an organization full of dreamers, but also engineers, scientists, physicists like myself, astronauts, doctors, and others who are prone to realistic, if epic, dreaming. It is an epic task, but not an impossible one, and the prize is a whole new solar system and all the worlds within it, which is a good motivation to keep doing it, and for your colonies, when they grow up, to do the same. Until we can pull this off, we don't know either way, but I think it is a big stretch to assume that intelligent life is common, and yet nobody, in all their existence, ever figures out how to make this work. Now, the other half of that from Fermi's perspective is the other late filter, that you are on a short timeline to achieve this because your civilizations wrecked themselves with advanced technology, but we will return to that. In the meantime, the optimism about space exploration that followed the Apollo program in the 1970s gave rise to another popular solution to the Fermi Paradox, and also gave the paradox its name. It is also the default explanation we tend to favor on this channel, though not without some caveats we've discussed elsewhere. This is the rare Earth hypothesis. It argues that the universe is as big as we think, and if intelligent life were common, and if space travel became practical, then even accounting for 90% of civilizations wiping themselves out before reaching the stars, the galaxy should still be wall-to-wall with interstellar civilizations by now, especially since in principle, nothing prevents intergalactic travel either. Given that emptiness, the rare Earth camp suggests the conditions for life, especially complex, intelligent life, must be much rarer than we assume. And this is where we get the idea of the Great Filters, critical steps between the formation of a solar system and the emergence of a spacefaring civilization. Some of these steps may be so difficult that passing them is like winning the cosmic lottery. A great filter could be a single, near impossible leap, or a series of many smaller but compounding hurdles. Even if there were, say, 30 tough steps, each with only a 50% success rate, the odds of making it all the way through would be about 1 in a billion. Some steps are likely minor, maybe 90% of civilizations can overcome them, but they still add up. Others could be major. The emergence of complex cells with nuclei, or the development of brains as sophisticated as ours, are often cited as likely candidates for strong filters. We explore these possibilities in more detail in our episodes on rare complexity and rare intelligence in the Great Filters series. And again, this becomes the default notion, not necessarily the right one, but our ground state, largely because of the next popular idea, that aliens just can't be heard. Now, there are a few subcategories to this explanation, including the dark forest theory, which suggests civilizations are afraid to transmit signals for fear of drawing attention and attack. But the core notion here is simpler. It is hard to pick up a radio signal from a tower 100 miles away, let alone 100 light years, so perhaps not many civilizations bother transmitting at all. In and of itself, that seems reasonable, especially if you assume interstellar colonization is undesirable or impractical. Even in a galaxy where nearly a million civilizations arise, you'd still have almost a million empty star systems between neighbors. That's a long way to send a signal. Over galactic timescales, it becomes even more plausible that single planet or single system civilizations might wipe themselves out or go through periods where no one wants to pay for a big transmitter that, after thousands of years, has yielded nothing. However, this idea falls flat in two big ways. First, people argue that a signal can't maintain coherence over such vast distances, but that is simply not true. Our regular signals cannot, the ones we use for high-speed communications, because they're designed to maximize data rate, not distance. Also, anything you do to compress a signal makes it look more like noise, since the point is to remove any repetition with a note saying so. Moreover, empty space is not perfectly empty. It's perturbed by gravity and other factors, but you can counteract that with higher power and lower pulse rates. After all, we can detect pulsars from immense distances. Take NGC 5907 X1, 50 million light years away, with a relatively slow pulse rate of 1.13 seconds. Even at that rate, you can send a lot of information, and inside the same galaxy, you could easily transmit text at the speed of human speech. Second, the power problem is outdated. Early assumptions were based on omnidirectional broadcasts and came from before we had discovered exoplanets. Today, you would use a tight beam aimed directly at the target planet or its orbital zone around a star. Those still widen out over distance, but it helps a lot. Personally, I'd figure out the planet's orbital period, the length of its year, and use that as the header for the message, 365. It would be a not-so-subtle way of saying, we know your address. Finally, even if all their signals are encrypted, weak, or local, we do not have to read the messages to know they exist. Much like spotting a sudden surge in encrypted emails, we should see an unnaturally high bump in radio emissions from a planet. And, over time, these anomalies will look increasingly artificial as we refine our observations. As I mentioned, this is the other classic Fermi Paradox solution, and like the first, it all falls flat in ways that reinforce the rare Earth hypothesis. Nothing stops them from transmitting. If colonization is impractical, they don't have to fear invasion, and even if they're silent, we should eventually spot anomalous radio emissions from exoplanets as our astronomy improves. This leaves two alternatives: Either they are too terrified to transmit, see our episodes on Dark Forest Theory for why that's a losing strategy, or they simply are not motivated. They could contact us, or even visit us, but the uncomfortable truth might just be humans are boring and they don't want to. The idea that humanity and Earth would be uninteresting to anyone else comes from a reasonable kind of self-deprecation, the belief that we are not the center of the universe or particularly special, and while that's an appropriately humble attitude, it is also a terrible premise. Pick the most boring spot in the US and it still gets visitors. I'm from Ohio, so I usually point the finger at Kansas instead, but truth be told, my beloved home state is often joked about as being pretty boring too. Yet for most of this show's history, I lived in one of our tourist spots, Geneva on the Lake. Quiet in the winter, but bustling enough in the summer that when I got married, we moved 2 towns over and bought a farm for a little more peace and quiet. Route 90 runs along the south side of that farm, the main trunk line for northern commerce across the continent, and it's a reminder that even a place that isn't exciting enough to stop at, it is unlikely that no one would ever pass through, pull over for a break, or check their tires. Fundamentally, it just seems improbable that curiosity would be a rare trait among advanced civilizations, and likely the smarter they are, the worse their curiosity would be. Even if we assumed we were no more interesting to them than insects, we have plenty of people here on Earth who devote their lives to studying bugs, and they don't exactly hide while they do it. Speaking of hiding, that's another common and deeply flawed solution to the Fermi Paradox, best known these days thanks to all the discussion around the Dark Forest Theory. It's popular because it is not boring. It makes for great storytelling. Sinister, ancient enemies lurking among the stars. Hostile galaxies where civilizations destroy each other at first sight. We've done deep dives on the arguments and flaws in other episodes, but the short version is this. Hiding because you're afraid a more advanced civilization will find and destroy you rests on 2 shaky assumptions. First, that there is an ancient, highly motivated enemy out there with the will and technology to wipe out civilizations across millions of years and quadrillions of miles, but oddly enough, they haven't bothered colonizing those places themselves. Second, that hiding would actually work. We'll come back to that first assumption in a moment. For now, it's worth focusing on the second. This scenario assumes you're facing an incredibly observant and capable adversary, one advanced enough to obliterate you from unimaginable distance, and yet somehow they're not investing in probes, telescopes, or early warning systems. They would have to predate you, otherwise they would be no threat, and the idea that they can only detect civilizations by obvious technosignatures, like radio waves, is outdated and flawed. They could spot life itself. I could name a variety of biosignatures like high oxygen or carbon dioxide levels, but the truth is simpler. Any life form, no matter how bizarre its chemistry, uses ambient energy flux to power its metabolism, and that leaves a footprint. Life changes a planet's atmosphere and surface reflectivity, altering its natural albedo. A species obsessed with wiping out life would be observant and thorough. Long before you ever built a radio telescope, they would have known your planet harbored life, and if they even needed to send probes every 10,000 years to check whether you'd reached a threatening stage, that would still be cheaper than sending armadas or doomsday devices. If doomsday devices are cheap, they'd probably just dispatch them alongside the probes anyway. The bottom line is that hiding is not a good strategy. The threats you're worried about have likely already seen you, and even if you never transmit a single radio signal, they'll find you eventually. And if you did transmit, well, without a time machine, you can't go back and erase it. Now that we've covered the basics, most of the theories left are really just attempts to evade or find exceptions to the points we've already discussed. One of the big lingering questions is whether civilizations even choose to colonize at all. We usually assume they would. After all, you can build a pretty nice home around almost any star. Whether populations always keep growing is a separate debate, but in biology, growth and expansion are the default. If you can grow, you do. And from that perspective, empty star systems would seem like prime real estate. The problem is, that impulse is biological, not necessarily logical. That's why even with space travel, most thinkers assume you would have to slow down population growth to avoid a Malthusian catastrophe. After all, it's a lot easier to double your numbers than it is to settle new planets without faster light travel. But that same logic might also warn a civilization that, without FTL travel or communication, all those distant colonies will eventually evolve into something else, distant cousins becoming, for all practical purposes, alien civilizations. And if history teaches us anything, it's that we have a hard enough time avoiding conflict with ourselves, let alone with true aliens. This could lead some civilizations to ban interstellar colonization, at least beyond certain distances. Instead, they might strip mine nearby systems for resources and then haul them back home, while deliberately making distant systems harder to settle, and even harder for rivals to build up into dangerous empires. I call this an Interdiction Bubble Civilization, or IBC. It's a newer idea I developed after revisiting the classic Interdiction Hypothesis, which suggested alien civilizations might leave buffer zones between each other to avoid conflicts or hybrid civilizations forming. I like this idea because even if they're building Dyson swarms around their home systems, we might not see them. They could maintain such large buffer zones that we're sitting in or near one right now, and that would explain why we haven't heard anything at all. And that's the real heart of the Fermi Paradox. It's not just about whether they exist, it's about why we haven't seen them yet. And the farther we look without seeing signs of life, the harder it gets to believe they're out there colonizing every star or sending out signals, and we're just somehow missing it. So that one came out after our most recent iteration of our Fermi Paradox Compendium, and thus isn't in it. And so is another we dubbed the Hermit Hypothesis, or Hermit Shoplifter Hypothesis. The idea is that civilizations with very advanced AI, life extension, or post-biological technologies might not have much reason to organize themselves anymore. If you can have your own personal spaceship that lands on asteroids to refuel itself, and can 3D print or replicate anything you need, and keeps you living in luxury, complete with convincing virtual utopias populated by simulated societies, then other people aren't much of an advantage. They're mostly a risk. After all, anyone else could replicate nuclear bombs just as easily. In this scenario, civilizations might tend to destroy themselves whenever too many people gather in one place for too long. Over time, this could favor small, low-density populations scattered across the galaxy, nomadic groups or even lone individuals living in deep space far from others, only occasionally returning to stockpile resources. Some might be travelers like you or me, wandering solo or with a family, maybe in village-sized communities. Others might be lone wolves, or massive post-biological intelligences, and probably a mix of all the above. Since large megastructures or densely populated civilizations would be prime targets for collapse anytime some lone lunatic decided to unleash WMDs, they would be rare and hard to spot, even if the galaxy was full of wanderers. This hypothesis is not without flaws, though. Lonely travelers might seem likely to seek out non-threatening civilizations like ours and say hello, but that would be quite rare. They might prefer to stay quiet, avoiding attention, and be reluctant to share technology, especially if they see no benefit in accelerating another civilization's downfall into the same nomadic wandering they've already embraced. Folks get lonely for real people, but will also tend to eliminate themselves faster if they do, as each interaction carries a statistical risk of death. It may be a 1 million chance, not Russian roulette, but if your aim is to live millions or billions of years, then the odds will catch up to you, whereas you could stockpile trillions or even quadrillions of years worth of fuel and go live in the intergalactic void. That brings us to another fun set of ideas that, unfortunately, do not hold up well under scrutiny: the Aestivation hypothesis and extragalactic migration. The idea here is that for post-biological civilizations, if you have a stockpile of energy, the longer you wait to use it, the more computation, or thought, or life you can squeeze out of each joule. Cold temperatures help with computation, and the universe is colder out in the extragalactic void or in the far future. So the theory goes, you either migrate to colder regions of space to maximize efficiency, or you go sleep and wait for the universe to cool down. or both. At first glance, both ideas make a kind of perfect sense, but problems pop up for civilizations very quickly. First, you wouldn't put your entire civilization to sleep and expect to wake up without leaving guardians behind, and if you trust those guardians, it's because you've rationally determined they're up to the task, which would mean they are actively monitoring the galaxy and possibly even gathering more resources to haul out into the void for future use. Maybe you've grabbed a mountain of supplies and launched off toward deep space, heading somewhere the Hubble expansion will eventually isolate completely for your protection. That is plausible, but you expect others to stick around too, and that's the real problem with both theories. Not everyone is going to pursue this strategy. Even if some civilizations estivate or migrate, it wouldn't take long, on a galactic timescale, for others to replenish their numbers and become visible or noisy again. Loud aliens, and possibly want to steal your stockpiles. Waiting out the universe seems clever, but not everyone's going to sit quietly and wait. The same reasoning applies to ideas like Transcendance and Ascension, evolving to a higher plane of existence, or migrating to a more fertile universe where the grass is greener. Many might make that leap, but not all at once, and plenty would likely think it's a bad idea and discourage their kids from trying. Still, this is one of the better sets of Fermi Paradox theories, because first, you've probably already sent your restless and adventurous types off on these journeys, and future generations would likely keep doing the same. Maybe you're growing your population by 2% a year, but you also have an effective 2% departure rate from people choosing to transcend or migrate. That might act as a kind of natural throttle. When your world or worlds start getting crowded, more folks look for a way out. The downside, of course, is that we have no direct evidence that other universes or higher planes exist, much less that we can travel to them, but we don't have any evidence against it either, and plenty of theoretical physics hints that they might. If they do, they could offer far better options than traditional space colonization. After all, why spend centuries on a ship bound for a dead planet when you could walk through a multiverse gateway to a copy of Earth, identical to ours but empty? And when you consider multiverse numbers, even our vast universe starts to look tiny. There would be more uninhabited but pleasant Earth clones out there than there are grains of sand in the entire universe. This brings us to another idea that falls flat, the notion of infinite miniaturization and ever-improving efficiency. The argument goes that if you can keep doubling how small or how efficient your machines are, and you can do it faster than your population grows, then you never run out of space in your virtual utopias. The flaw here is it assumes an eternal Moore's law, but Moore's law was never a true law of physics, just a short-term rule of thumb. Infinite improvement in efficiency is not science, it's more of an article of faith. Even if we grant it, not everyone is going to want to miniaturize themselves or stay behind. And all that constantly improving technology is eventually going to let you either migrate easily to other star systems, or send out robots to harvest them for more resources. Either way, you end up as a loud alien civilization, and break the Fermi Paradox. And this is also a problem for another class of theories, rogue AI and Berserkers. If the machines are competent enough to replace their original creators and spread across the galaxy, they are not a good Fermi Paradox solution either. If they're too dumb or too unmotivated to expand, maybe. That brings me to the last Fermi Paradox solution I actually like for today, the notion of zombie AI and Berserkers. You could intentionally make them fairly dumb, something we might invent even before real general AI, and we still know so little about how an AI just a bit smarter than today's systems, but not human level, would behave if left to drift in space. It's not inventing anything radically new, it's more like trusting simple rugged systems to colonize the galaxy ahead of you. They wouldn't be building giant Dyson swarms, just basic infrastructure so that when you do arrive, you have power and resources waiting. You could have an entire galaxy full of such relics, or old IBC patrol fleets gone rogue and never even notice. They may not have engines powerful enough to land on planets, just slow, high-efficiency ion drives and similar tech used for harvesting asteroids. It's not the strongest theory, but its weaknesses overlap with what we don't know about AI behavior, and that means they might not be weaknesses at all. And our last idea for today asks whether aliens might be so alien that they're simply unrecognizable, so different that they could stand right next to us and we wouldn't realize it, maybe vice versa too. It's hard to prove or disprove a theory like this. I would argue, as always, that the burden of proof lies on the extraordinary claim. Extraordinary claims require extraordinary evidence. But more than that, I believe intelligence recognizes intelligence. Just as we can spot life, even life using different chemistry, because it inevitably alters its environment to survive and thrive, intelligence does the same, only more so. Life spreads out to absorb sunlight and changes a planet's albedo. Intelligence, by nature, calculates and optimizes, leaving even clearer footprints. Sure, you might mistake a random alien tool for a random rock, just like you might mistake an old stone axe or arrowhead for a natural stone, but walk into a whole workshop full of tools, and you know immediately, this was no accident, this is not random. Intelligence recognizes intelligence, and for that reason, I think this theory falls flat. And that will wrap us up for today. Honorable mention goes to the simulation hypothesis, but it isn't falsifiable, and it doesn't really give us an in-universe explanation for the Fermi Paradox. If you're interested in more on the topic, it's probably our favorite after space colonization. We've got not only the big Fermi Paradox compendium, a great intro to all the major terms and solutions, but also deep dive episodes exploring dozens of them in detail. We just hit our 500th weekly episode, and thanks to all the bonus and spontaneous episodes like this one, we are actually somewhere around 720. A lot of those cover topics like these and many more. We do not do clickbait titles here, so if you are new, feel free to browse around. Whatever the title says is exactly what the episode is about. And if you enjoyed this, like and subscribe so you get alerts when we tackle more for future episodes. As always, thanks for watching, and have a great week.